Good afternoon, everyone. Thanks for having me here. Today, my presentation topic is floating solar in the United States, like for reservoirs. We want to discuss about regulatory, environmental, and economic potential for those floating PVs. My name is Mucun. Currently, I'm a power system engineer at Idaho National Laboratory. Currently, I'm the PI of a couple of principal investigator of a couple of projects funded by Department of Energy's Water Power Technology Office, Solar Technology Office, and Wind Technology Office. First, thanks for the partners in this project. From ILSN, our team, like Tenweir, Tyler, and Juan. So Tenweir is mainly focusing on solar generation and grid integration piece. My colleague, Taylor, is focusing on the development of techno-economic assessment for all of the floating solar projects across the United States. I'm a data guy, so I'm mainly focusing on resource and electricity price forecasting. Juan is a PI for this project, and it's a collaborated work with National Renewable Energy Laboratory, Oregon State University, floating solar PV design and industry partners, DNV, Eagle Creek, and Cat Creek. They are asset owners and operator partners for floating solar. So in this project, our objective is to provide a foundational data and analysis to stakeholders to accelerate the floating solar power plants deployed in the United States reservoirs. So our stakeholders can be, as you can see here, policymakers, regulators, developers, utilities, NGOs, and also financial firms. Specifically, our analysis will focus on 4 areas: regulatory, environmental, resource assessment, and techno-economic assessment. Our deliverable will be like this. For example, we want to have a tailored floating solar specific techno-economic assessment and environmental assessment too. Because before a project starts, we want to understand from the technologic side and economic side, if that is viable or not. Also, we want to understand the regulatory, environmental, and stakeholder opportunities and challenges to identify the clear regulatory and environmental pathways to siting all of the floating solar power plants across the United States. In addition to that, we try to build up a novel high-fidelity geospatial resource assessment work to estimate the floating solar power plants technical potential on reservoirs in the United States. We performed 3 case studies on both open-loop reservoir with traditional hydropower plant, closed-loop reservoir with a proposed pump storage hydro plant, and with a floating solar PV system designed and modeled for each site. So, on the right-hand side, there is an illustration of the floating solar power plant. As you can see, these solar panels are floated on the main body of this lake. Before starting a project, we have conducted a stakeholder engagement through a PAC because we want to answer 2 key questions. First is that how important is a regulatory and environmental assessment for floating solar power project, floating PV projects, and how that affects it. And will techno-economic assessment help build up this kind of floating solar projects? And this stakeholder engagement will include developers, NGOs, and asset owners to answer this question. And we asked them what reaction have them heard from stakeholders about outputs or findings. From positive side, they mention the regulatory and environmental assessment could help pathways for deployment. That means it's very important. However, for the negative side, the techno-economic assessment analysis so far is not enough to help developers beyond what they have. That doesn't necessarily mean the techno-economic assessment is not important, but that means probably we need a better techno-economic assessment for those floating solar power projects to make it more generalized and easy to be used for our stakeholders. So here are the bottom line up front. From this project, the biggest achievement to date, we are development of a framework for a tool. The tool is called EcoPV. Later, I will share like the link and the interface and introduce about this tool. It's already online, and we have already got a regulatory pathway memo, and we also have a geospatial methodology and data set included in the EcoPV. We call this tool called EcoPV. And priority for the future, we will perform like FPV and hydro schedule optimization, try to optimize the revenue. That means like the power generation with co-located floating solar PV with hydro plants, considering day-ahead market and real-time market, optimize the revenue. And we also try to perform sensitivity analysis of different energy markets, because those projects located in different ISO and RTO regions, they have different incentives and market structure. And for this public beta version of EcoPV, it has been already published. Here is a general overview of the EcoPV tool. This is it's a web-based tool, so probably it's pretty small here. It has different modules. This is a homepage, and this is like techno-economic assessment module, and this is an environmental impact module, and this is a solar generation module, and this is a capacity design. Specifically, we will have floating solar power site specifications to initialize the design. With this information, we can build like a floating solar PV system layout. And after this information is decided, we can go to the PV lib. It's a wrapper through EcoPV to calculate the solar power generation time series. And with that information, we can have a planned AEP, and that goes into directly to the techno-economic assessment module. And that will generate a couple of important metrics, such as ROI, payback period, LCOE. Those are our stakeholders are interested in. Using this floating power layout, we have an environmental module that will have feedback to user-specific percentage of coverage used to determine the feedback to our like floating PV system layout here. Here is the initial design for like one example from category floating PV, and this is like a example of a solar power generation from the floating PV sites. This is an example for Tuckerton. It can produce like around 100 megawatt hour, more than land-based PV of the same capacity in 1 year. So that's really a lot improvement on that. In our tool, we also have like US reservoir floating PV capacity listed in a US map. And this visualization can help our stakeholders to understand what's the capacity across the United States for our current existing floating PVs. Then comes to like the techno-economic assessment module. We have like a 33 megawatt co-located FPV installation. And the CAPEX and OPEX are given in the previous slides. And we consider the upfront incentive included like 10%. And right now we consider like average yearly incentive is like 50K for the continuously like 15 years. And as you can see, here is the interface, and we have the payback period calculated. Now, comes to like how does the floating solar power, the floating PV affect the reservoir's environmental and ecological conditions. We have like two very fancy animation here shows how that affects. As you can see, as time goes by and the distance, the x-axis is the distance of like the downstream size, and the y-axis is a reference reservoir we used and a 12 segment FPV. As you can see, with the floating solar on the top of the lake as the shaded segments, the water temperature is much lower than the reference reservoir without co-located floating solar with hydropower together. In addition to the environmental impact, we want to provide a long-term techno-economic assessment with uncertainty quantified. So by doing that, we can understand how the floating PV revenue differs from different electricity markets. So we try to generate long-term locational marginal electricity price forecasting to calculate the revenue. That can be served as an indicator for economic assessment and also can perform long-term cost-benefit analysis. On the right-hand side is like a 40-year ahead electricity price at a specific IO is like Duke Energy from Carolina. This is a long-term electricity price probability forecasting. Instead of provide just a single point forecast, we provide prediction intervals, and those help our users to make decisions. After that, we perform a case study on different market and different tax credits. In the previous slides, we have a probabilistic forecasting generated, and this probability forecasting model is trained here. Our inputs are long-term weather forecast, historical weather observation, and historical electricity price. Those three information can be grabbed from different ISO and RTO's official website. With these inputs and model, we can get massive long-term electricity price scenarios. And these scenarios will be used together with the calculated energy generation to calculate the revenue. And also, this revenue plus the incentives provided by the government, state incentives and federal incentives, we will come up with the final financial metrics, including the payback period, ROI. Next page is like the case study results. On the bottom side, here is an animation of the long-term electricity price scenarios at California, at Castle. So we generate like 100 scenarios, just illustrated here. The blue line here is a deterministic forecasting, and this rainbow color is just 100 scenarios. On the right-hand side, we plot the LCOE and the payback metrics. We found that the LCOE and the payback metrics are sensitive not only to different markets, but also the selection of solar incentives. For example, the incentives we have a PTC and ITC or no incentives. And on the right bottom side, we have the payback period plotted based on different incentives and different ISOs. We find that the key takeaway is that the payback period is generally like faster with a PTC or an ITC incentive. Now here comes to one of the probably most important things. What regulatory and environmental pathway to floating solar power do we have available today? First information is so important. The FERC hasn't authorized any floating solar power development at existing FERC licensed hydropower facilities. That means all of these FERC licensed hydropower facilities cannot develop any floating PV themselves directly. However, they authorize the ground-mounted solar PV with FERC license boundaries. That gives us a solution. That likely provides the regulatory pathway for adding floating PV and existing fertilized hydropower plants. By doing that, we can have like a co-located floating PV and hydro plants together. Also, the USBR and U.S. Army Corps of Engineers do not have the authority to develop floating PV at federal facilities. Both agencies only have a congressional authority to authorize private third party to develop FPV. Also, both state and federal regulators have concerned about the PV panel, their toxicity and water quality impacts that could result from floating solar installations. These informations are very important. However, many stakeholders doesn't know that even before they started projects. So that's a main reason why majority of floating solar power projects are canceled or stopped after they start. Next, I want to explain a little bit how do we determine the technical potential of floating solar in the United States reservoirs. Our inputs are US ACE locations, USBR locations, and FERC locations, and water body polygons plotted on the map. This floating PV information are used as spatial cross-referencing, and we can generate federal water body polygons, and then water body spatial exclusions. And with a specific study area of water body polygons, we can have a raster processing and develop area and capacity estimates. This will be illustrated on our tool later. Here comes the illustration of previous slides. So we plot the technical potential of floating PV in the United States reservoirs on the US map. We have like different spots, circles here stand for their water body capacity. The bigger the circle is, that means the bigger the water body capacity is. As we can see from here, the potential capacity by water body type, like USA's, USBR, and FERC is listed here. And right here, the data is shown for the most conservative assumptions that doesn't sum to a total due to a water body categories as multiple categories. Here's a summary of a developed area criteria. For our inclusion criteria, we want to have the water temperature, navigable, and ownership. And for our exclusion criteria, we will have like depth, water current, mooring, and distance from them. Those ones we don't want to include. So I won't go into too much details there because I will share the slides in the presentation. Here is a total technical capacity of like 700 gigawatts for floating PV across the United States. There's a 27% average coverage area and 1.4 gigawatts average individual reservoir capacity. On the left-hand side is the percentage coverage of included reservoirs, and on the right-hand side is the capacity at included reservoirs. As you can see from here, when the percentage is like 0, the huge number of reservoirs here, and the main percentage is like between 10 to 40%. Then, what's next? For our development of Aqua PV project, we want to have a full integration of environmental database included, and try to perform PCA analysis to select different environmental modes. And we will integrate our tool with the PV lead based on our user-specific system, generate the machine readable system. As I mentioned at the very beginning, we try to have a high-fidelity PV generation for any US location integrated in the economic assessment portal. We have already published a beta version, and we also have the high-level analysis using the technical potential and disadvantaged communities with GIS layers. Yeah, that's all. Any questions? Yeah.
So you touched on panel toxicity and water quality concerns. You didn't touch on wildlife impacts at all. So I'm just kind of curious, when you look at a traditional solar farm compared to a solar farm that's floating on a reservoir or body of water, what kind of difference in impact do you see to birds per megawatt killed in comparison?
Yeah, I think that's a very, very good question. Actually, when we started this project, yeah, people with the stakeholders has already asked the same question like you have. These ones are something we try to include in our upcoming revision of the AOP of this project. So right now haven't included yet, but we will include that in the future. Yeah. Yeah.
So you talked about these floating EVs at reservoirs. Have you considered looking at other industrial ponds like cooling ponds, thermal generating stations, or other industrial facilities that have these ponds that they use that might be less environmentally sensitive?
Yeah, that's a very good question. I think those options initially they're proposed, but I think for this project is mainly for just the floating solar with hydropower plant itself, because in the US there are already so many like floating PV projects, existing floating PV projects. However, these projects have some issue. So the objective of this project is mainly help them to go to the correct way and help them to better understand the techno and economic of the existing project. So I think what you mentioned is like another trajectory of this project, but yeah, have included. Yeah.
What's the biggest challenge with maintaining these when they're floating on water?
Yeah, good question. So the biggest challenge for maintenance this floating PV is the project. Yeah, because it's directly exposed to not just to the sun, but it's also like on the top of the water. So the project is the biggest challenge to maintenance this kind of project.
I have a question on, again, back to toxicity. What is the chemicals that get dissolved in the water, and how bad are they for the agricultural? Mostly it's for agricultural, right? The canals. You don't use that water for drink. You don't put that on drinking water. So how does it affect farming?
Okay, so the majority of how that affects farming is more on the regulatory side. So for example, if you have a floating PV built on upstream, you have to consider different environmental constraints. So that constraint include like flooding constraints, recreation, boating, water flow constraints, and also the agriculture and irrigation constraints, as you just mentioned. Because when you add this floating solar, those constraints need to be need to be modified somehow. Yeah, they can't be original constraints anymore, because the capacity increases, and also, for example, you have a floating PV on the top of the water. In previous animation, it will affect the water quality and all of the flow limit, flow rate, and ramp limit. Yeah, affect all of them.
So what chemicals leach out? What kind of chemicals leach out in the water?
Yeah, to be honest, I don't know what a chemical. Yeah.
Stuff.
More questions? Okay. If not, welcome to next.
Yeah, thank you.
Thank you.